Hello and welcome back. This video will start section 3.2, which is all on graphing polynomial functions. So to begin with, a polynomial function is one that looks like this right here. And if I go through the pieces of this really quick, each part of this is just going to be some number, which I've called, say, a sub n or a sub n minus 1, all the way down to a sub 2, a sub 1, or a sub 0. It's going to be some number times x to a positive power. So we have some number times x to the n, some number times x to the n minus 1, all the way down to some number times x squared, which is x to the second power, or some number times x, which is the same thing as x to the first power, and a0, which is the same thing as something, a0 times x to the 0 power. Anything to the 0 power is just 1. And we just leave that off. Polynomial functions will look like this. It's just a sum of a bunch of terms, and all the terms have x to some power. So very quickly, when we look at a function like this, when we look at this, we go, okay, so let's see if this is a polynomial function. We see that we have x to the fifth power times the number, x to the third power times the number, and then no x is here. So this is a polynomial function. And then the degree of the polynomial is the highest power of x, which is 5. And the term with the x to the fifth power, this degree, this is called the leading term. And we'll see that leading terms are very important in understanding what this function looks like. Since this has the highest power of x, this term is going to dominate the function when x gets really big. If we look at this next function here, this is not a polynomial function. Since this first term has a square root of x. And if we rewrite this, we can rewrite this as x to the 1/2 power times the square root of 5 times x to the third plus 3. And x to the 1/2 power, this here is not an integer. So this is not a polynomial. And the same thing goes in this next line. Even though we have an x squared, if I write this as x to a power, anything on the bottom of a fraction is just like a negative exponent. So here I have x to the -2 power, and -2 is not a positive integer, so this is going to be not a polynomial function. This last one doesn't necessarily look like a polynomial right off the bat, but if I distribute, I can have 2 times x to the fourth times x to the third. Well, this is going to be 2x to the seventh. And if I multiply it by this last term, I'll have minus 10 times x to the fourth. So after I distribute, I get this, and now this looks like a polynomial. The degree, the highest exponent on the x, is going to be 7, and our leading term is going to be 2x to the 7th. So a couple of nice properties. Sorry, before I get into that, we've seen linear functions before. This is just going to be mx plus b that we've seen before. Something times x to the first power plus a constant. And likewise, a quadratic function is one that looks like a quadratic equation, where we've got a number times x squared, a number times x, and a constant term. So we've already seen linear and quadratic functions and seen how to graph these. So one thing that there's two rather important properties of graphs of polynomials. One is that they are always smooth. There are never any sharp corners, and they're always continuous. So as you draw a polynomial, you should find that essentially your pencil should glide across the page. We're never going to lift up the pencil and move it somewhere else, and we're never going to make any sharp sharp corners. So both of these are examples of polynomial functions, whereas something like this, where in this function, if we trace this function, we're going to have to lift our pencil up, bring it down here, and continue tracing it. So this is not a polynomial. This is certainly not a polynomial because I have to lift my pencil up to get it from one side to the other. This is in fact a familiar graph. This is the graph of the absolute value of x. And here we've got a sharp corner right here at 0. And that sharp corner means that this is not a polynomial function. And in fact, since we know what it is, we can easily see that this is not a polynomial. This isn't just x to some power. We've got an absolute value in there. So the other thing that we'll see in this video is going to be end behavior for functions. And what end behavior is what the function looks like to at its ends, meaning what happens far to the right and far to the left. So if we let x get bigger and bigger and bigger as we move farther and farther right, the question is, what happens to the function? Does it go up? Does it go down? Does it stay constant? Does it go back and forth? Also, if we go very far to the left, as x gets more and more negative, going past -10, going past -100, going past -1 billion, what happens as x is going further and further to the left? Is it going up? Is it going down? Is it staying constant? Is it wiggling back and forth? So this is just the end behavior of the function. What happens to the far right or far left? And when we look at a polynomial function, again, this is anything that's something times x to the n plus something times x to the n minus 1th power all the way down to x squared. We've got an x term and a constant term. The end behavior is determined entirely by the leading term. So this is the only term that you have to look at in order to see what is the function going to do as we go farther to the left and farther to the right. So let's look at a couple of examples and see what exactly is going to be happening for various things. So when n is odd and that leading coefficient is positive, we could have something like f of x is equal to x. Remember that x is just the same thing as 1 times x, but we don't normally write the 1 times x. We know how to graph this function. The x-intercept is 0, the y-intercept is 0, and we just get a function that's just a straight line going up and to the right. So the end behavior, far to the right-hand side, we're going up. Far to the left-hand side, we're going down. Or coming up from the bottom. Whereas if I put a negative sign out here, and I still have that first power is odd, so again, one way I could write this would be -1 times x to the first power, and 1 is an odd number. So this function is going to look like this. Again, remember that when we take a function and we multiply it by -1, as in we add a negative sign, we're flipping it over. So here, we're coming down far to the left, and we are continuing going down as we go farther to the right. So here's a couple of examples as well. So here we have the function 2x to the third minus x squared. So the important facts here, our leading term is 2 times x to the third power. Our exponent is odd, and our coefficient is positive. So what does our function do? As we come further and further right, we're going up. And over to the left-hand side, we're coming up from -infinity. Notice that this is the same thing that's up here. As we go further to the right, we are going up. And as we come to the left, we're down here. Whereas with this leading term, we've got -2x to the fifth. This is our leading term. Again, our power over here is going to be odd, but now our coefficient is going to be negative. So what does the function do? As we come further and further to the right, we are going down. And when we look over here to the left, we see that we're coming from the top. So if I wanted to describe the end behavior, if I have a positive coefficient but an odd power, whatever my function is, I'm going to be going up over here, and I'm going to be coming from the bottom on the left-hand side. Whereas if our power is odd, but our coefficient is negative, we flipped everything. So as we go further and further to the right, we're going to go down, and we're coming from the top if we're going from left to right. So this is going to be the end behavior that we'll notice. We will see something slightly different when n is even. So for instance, if I need the leading power, the degree of the polynomial, to be an even number, let's look at x squared. Well, we know what this looks like. So when we have f of x is equal to x squared, this looks like this. We have a parabola that opens up. So our end behavior is going to be, well, we're coming up as we go further and further to the right. And over here, we're coming down from negative infinity as if we're coming in from that left-hand side. If we flip this over and we make everything negative, we've just flipped the whole thing over. As we come to the right, we're going down. And as we come in from the left, we're coming from negative infinity. We're coming up as we follow our function. And this is true in general. So down here, so for instance, our leading term is going to be x to the fourth power. We have an even power, and our coefficient, which in this case is going to be 1, is positive. And you'll notice that it looks the same as our parabola. We're coming up over here, and we were coming from the top down as we go from left to right. Likewise, over here, when we have negative 3 x to the sixth, when we're looking at the sixth, we have an even power, but a negative coefficient. So our function is coming down as we go further and further to the right. And if we're going to the left, we're going down. But if we do this correctly and we think about what happens as we go from left to right, we're coming up from the bottom, coming down. So our end behavior, our end behavior, when we have an even power but a positive coefficient, is going to look like this. Who knows what this will do in the middle? It'll wiggle around, but toward the end, it's going to be coming up. Whereas if we have an even power and a negative coefficient, our functions are going to be pointing down in both directions. And again, who knows what's going on in the middle, but what we know is the end behavior is going down. And I'll continue this idea in the next video.